Hello and welcome to today's video. In this video we're going to discuss a very special sequence, Euler's sequence, and we're going to derive a relation that allows us to define Euler's number and in turn the exponential function using that sequence. So this section is titled Euler's Number. Now, what we're going to do is we're going to look at the sequence that we have seen before. That is the following. So we will study the sequence AN defined as 1 plus x over n to the power of n. And we will consider x a fixed number. And to make the technicalities a little easier, we'll assume that x is a positive number. Now, basically all the results that we will get can also be derived for arbitrary real numbers x. But things are getting a little more technical if we do that. So we try to keep this simple. Basically, I'm interested in showing you the principle and then giving you the final results of that one. So first goal is to prove that this sequence is actually converging. So we will show that the sequence AN with index n in n0 is converging. And to do so, we'll use one of the theorems that we've derived. Specifically the theorem that says a sequence that is monotone and bounded is converging. So to apply the theorem, we obviously need to prove that the sequence is monotone and bounded. And we'll start with monotonicity here. So the first thing we're going to show is that AN defined as 1 plus x over n to the power of n is increasing. Now, to show that a sequence is increasing or decreasing, there's basically two techniques you can apply. You could look at the difference of two subsequent elements, and we did that before. Or you could look at their ratio and then compare that to 1 to see whether the sequence is increasing or decreasing. That is what we're going to do here. So we're going to look at the ratio of AN plus 1 to AN. Now, AN plus 1 is 1 plus x over n plus 1 to the power of n plus 1. And AN is 1 plus x over n to the power of n. To simplify this, let's try to find the common denominator for both expressions. So in the case of the numerator, that will be n plus 1. So we can write that as n plus 1 plus x over n plus 1 to the power of n plus 1. And for the denominator, the common denominator will be n. So there's n plus x over n, and we're dividing by the denominator. So we're multiplying with its reverse. And that means we can just write this as times n over n plus x to the power of n. Now we still have these different powers, n and n plus 1. Of course, it's much easier if we have all to the same power. And to do that, we can either try to factor out one of these here, or we can take this to the power of n plus 1 and then divide by one of these. We'll do the last because it will turn out that will give us an easier result later on. So what we can do here is we can divide by this expression once, or multiply by the reverse, so we can multiply by n plus x over n. And then just have all of these here in one fraction. Raised to the power of n plus 1. So we raise this here to the power of n plus 1, divide by this expression to make up for that. And then we can write this and that on one fraction that is then raised to the power of n plus 1 for all factors. Now in the following, we'll just keep that factor here in front as it is. And we work with the factor next to that. So let's first simplify that a little. That expression here in the numerator, that is the same as n squared plus n plus nx. The expression in the denominator, this here, that is the same as n squared plus n plus nx plus x. So as you can see, that's almost the same. So this expression is the same as this part here, but the plus x is still something that we don't like a lot. So if we want to cancel out something in this fraction, we'll have to extend the numerator by adding x. And of course, to make up for that, we will then have to subtract x once again. So with this little trick, we can rewrite this expression here. Again, we copy that first fraction. We only change the second one. And now we can cancel out this part here and then just split off that second part. So what we get here is 1 plus minus x divided by n squared plus n plus nx plus x. And again to the power of n plus 1. Now why did we do that, you might ask? And the reason for that is we want to apply an inequality now. One that we've talked about in the very beginning. We want to apply Bernoulli's inequality. Now remember, Bernoulli's inequality says 1 plus x to the power of n is larger or equal than 1 plus nx. And we're going to apply that to this expression here. Of course, our n is now n plus 1. The x here is now exactly this expression, but otherwise we can apply Bernoulli's inequality. And if we do that, what we get is, again, we copy that first part here. And then we get this is larger or equal to 1 plus. And now we take in this power here, n plus 1, times, and now this expression here. So we just copy that, minus x over n squared plus n plus nx plus x. And we got rid of the power. And that, of course, makes things a lot easier. So again, we copy the first part. Let's have a closer look at that second part. What we can do here is we can, of course, move out the minus sign. This one here, we take that here. And we take that n plus 1 into the fraction. So we get n plus 1 times x. And for the denominator, let's do a little work on the denominator as well. If we look at this here, we can factor out an n here. So that's n times n plus 1, the first part. And that second part, we can factor out an x here. So that's plus x, again, times n plus 1. And that will enable us to cancel out the factor n plus 1. So if we're doing that, what we're getting is 1 minus x over n plus x. And that already looks a lot easier. So let's again try to simplify that by writing it as one fraction. So we have n plus x over n times the common denominator here is n plus x. So 1 is the same as n plus x over n plus x. And then we have this minus x here. And you can see that nicely works out here. So this is n plus x over n times, and now this plus x minus x cancels out, and we're left with n over n plus x. So all in all, this is exactly equal to 1. So effectively what we have shown here is an plus 1 over an is greater or equal to, with a lot of steps in between, but in the end we got a 1 here. And we need greater or equal to because at one point here, remember we've used Bernoulli's inequality to derive this greater or equal to here. So of course, if the ratio is greater or equal to 1, then the numerator has to be greater or equal to the denominator. So an plus 1 is greater or equal to an. And that means the sequence an is in fact increasing. So that's one of the two things we needed to prove. The sequence is increasing. The second thing that we need to prove is the sequence is bounded. So next we're proving that this sequence here, 1 plus x over n to the power of n, is bounded. We do this in two steps. First step is we're going to simplify our proof a little. Let's say we have a fixed x. Well, we can choose our index so high that x over that index, so this second expression here, becomes less or equal to 1. So for fixed x, let capital N be an index in n0. Sufficiently large such that x divided by capital N is less or equal to 1. And let's say k, we define k as n over capital N. Then we can write an as a times k capital N. So this whole expression becomes 1 plus x over kn to the power of kn. Not a lot changed yet. What we can use now is this relation here. X over n is less or equal to 1. So there's an x over n here. So that's less or equal to 1. Meaning we can say this is less or equal to 1 plus 1 over k. So the k stays, of course, to the power of kn. And this in turn is the same thing as that sequence 1 plus 1 over k to the power of k to the power of capital N. Remember, capital N is fixed, so that doesn't do anything to the sequence or to its limit or to the fact that it converges or not, or to the fact that it's bounded or not. What is interesting is the behavior of this part here. So what we've shown is if we can show that this part is bounded, then the original sequence, this one here, will also be bounded. So that simplifies matters a little and means it's sufficient to show boundedness for x equals 1. So it is sufficient to show that 1 plus 1 over k to the power of k is bounded. And in the second step, we're going to show just that. And we're going to do this in the following way. This expression 1 plus 1 over k to the power of k, that can be rewritten using the generalized binomial formula. So here we don't have a square, but a power of k, but that does not really matter. There's also a formula for general powers. And basically that says we have a sum. Let's take an index I here. That goes from 0 to that power, k. The coefficients are k over I, the binomial factors here, times, and now we have that first summand here, the 1 to the power of k minus I. So the powers of that are decreasing with increasing I. And we have that second factor, 1 over k. And the power of that is then increasing with increasing I, so to the power of I. So that's a generalization of the binomial formula. Again, we've talked about this before. So here we can apply that. Now, this binomial expression here, so those binomial coefficients, k over I, that can be expressed as saying this is k times k minus 1 times k minus 2 and so on until we have collected enough factors, and the number of factors is governed by this part here, so we need I factors, and that means we need to continue this up to k minus I plus 1, because we started at k, not at k minus 1, right? So this counts as well. So here, what we need is exactly I factors of that sort here. And then we need to divide that by I factorial. And then we still have these expressions here. So I to whatever power is always 1, 1 to whatever power is always 1. And 1 over k to the power of I is, of course, 1 over k to the power of I. So we can just multiply this by k to the power of I here. Now again, let's simplify this a little. Let's first take out the 1 over I factorial here. And then these expressions here, we'll split up the k to the power of I into k times k times k, and we have I factors. So each one of those goes with one of these factors here. That means we can just write this as times k over k times k minus 1 over k times k minus 2 over k, and so on up to k minus I plus 1 over k. And now what we need to see here is that each of these factors is in fact less or equal to 1. So we can just derive an upper bound by saying, well, this is less or equal to the sum from 0 to k 1 over I factorial times 1 times 1 times 1 times 1, yeah? So going one step further, let's split out the first summand, the one for the index 0, that is 1 over 0 factorial, that's just 1, plus the sum, I from 1 2k 1 over I factorial. And finally, we need to do something with this I factorial here. Remember, I factorial is 1 times 2 times 3 and so on up to I. So disregarding that one factor, we have I minus 1 factors that are each at least 2. So that means this is greater or equal to 2 times to the power of I minus 1. So for that sum expression, we can say 1 divided by I factorial is then less or equal to 1 plus that sum from 1 to k, 1 over 2 to the power of I minus 1. And now we're almost done. Let's do an index shift to start from 0 again. So instead of going from 1 to k, we can also go from 0 to k minus 1. And then, of course, we'll have to take 2 to the power of I. And that's, of course, the reason why we're doing that. What we want is we want to get back to a geometric sum because we have a formula for that. So we can evaluate this expression. So that's 1 plus. And this geometric sum is 1 minus this expression here to the power of this plus 1. So that means we have 1 over 2 to the power of k divided by 1 minus just this coefficient here, 1 over 2. So evaluating that, what do we get? Well, we have 1 plus 1 minus 1 over 2 to the power of k, and 1 minus 1 over 2, that's 1/2. So we have 1 plus 2 times something. And this here is sure to be greater or equal to 1. To 1/2, sorry. So what we get is 1 plus something that is at least 2 for large enough k. So this is bounded by 3. The worst thing that could happen in terms of boundedness is this factor here just vanishes, and then we get 1 plus 2, and that's 3. So we finally seen that that an is in fact bounded. It's bounded above, and it's increasing, so it's also bounded below by just the first factor, a0. So what that means is, together, we have seen that the sequence an, defined as 1 plus x over n to the power of n, is bounded and monotone, and thus it is convergent. So we know it has a limit, and that justifies the following definition. We just give that limit a name. You can, of course, try to compute that limit. It turns out that's not a very nice number, at least in terms of decimal expansion. That's not a very nice number, 2 to 0.7 something. But we can just give it a nice name because it will turn out this sequence appears fairly often in applications. And we'll later see some more hints as why to this might be the case. So this number is really important in many applications and in many areas of mathematics. The sequence an n0 with an being 1 plus 1 over n to the power of n. This is called Euler sequence. and its limit is called Euler's number. And this number is denoted by the letter E, like this. So our definition here is E is defined as the limit of 1 plus 1 over n to the power of n. Furthermore, we can define a function that uses that limit. That will be called the exponential function. So the function, we'll call that exp. It's defined on the real numbers. As I said, we can prove all this for the reals as well. Defined by, well, the exponential function of x is defined as the limit of the sequence 1 plus x over n to the power of n. That is called the exponential function. And just as a side note, one can show that indeed the exponential function of x is the same thing as the number e to the power of x. So it is indeed an exponential function. So that defines Euler's number, that defines the exponential function with base Euler's number. And as I said, this is one of the most important functions that we'll encounter in all of mathematics. And it will turn out later that it has some really nice properties in many central areas and lots of applications. We're going to see one of the applications in the later videos as an application, as an example of sequences. And afterwards, we'll turn our attention to more special sequences that are called series, and we'll investigate their specific properties. As usual, I hope I'll see you then.